In order to understand how a chip calculates, we first need to understand some elementary logic functions, namely the logical AND, the logical OR, and the logical negation. These logic functions operate with truth values called true and false and are denoted by 1 and 0 respectively. The logic functions AND and OR are both functions of two variables called inputs and one result called the output. The logic function negation, on the other hand, is a function of one variable and has one input and one output. The respective operation between the two variables is represented by this symbol for the logic function and by this symbol for the logic function OR. The negation is depicted as this symbol. The logical AND is only true when both inputs are true. This can be checked in the so-called truth table. On the other hand, the logical OR is true if at least one of the inputs is true. The truth table of the logical negation has only one input column. The result is true if the input is false, and vice versa. A theorem of logic says that any logic operation of variables, also called a Boolean function, can be written in terms of these three operators introduced above. We will now turn to the question of how these operations can be realized electrically, by means of certain switches. For this purpose, we will let the truth value true denote a current is flowing, and the truth value false denote no current is flowing. There are different types of switches: mechanical, electromechanical, vacuum tubes, and transistors. The mechanical switch is operated manually. It is thus very slow and not suitable for fast switching. The electromechanical switch, or relay, was invented in 1836 and was first used in the telegraph apparatus of Samuel Morse. When the current is on, the electromagnet becomes magnetic and attracts a plate to close the switch. When the current is turned off, the electromagnet loses its magnetism and the plate is returned to its initial position by a spring, opening the switch. The vacuum tube was invented in 1904-1905. An evacuated glass bulb contains the cathode emitter and the anode. The potential existing on the grid influences the electron flow from cathode to anode. If it is stopped by the grid, the switch is opened, and if it flows through the grid, the switch is closed. The vacuum tube was the first switch with no moving mechanical parts. Its response speed depends on how fast the grid potential can be changed, so it can be changed with electronic speed. The disadvantages of the vacuum tube are its failure susceptibility, its short lifespan, and its high energy loss due to the production of heat. Finally, in 1947, the transistor was invented. Here, the electrons do not flow through a vacuum or a special gas, as in the vacuum tube, but through a semiconductor, usually silicon. By doping the silicon with alien atoms, one can create regions with a surplus of electrons and others with a shortage of electrons. Between such a source and sink, there is a gate insulated by a layer of silicon oxide. By means of the potential applied at the gate, electrons either flow from the source to the sink, the switch is closed, or they don't. After about 1959, one began placing several transistors on a silicon disk, the chip. Now they were no longer little hats with 3 legs. Thus began the gigantic success story of integrated circuits. How can the elementary logic functions AND, OR, and negation be achieved with the operators introduced above? To keep things simple, we will explain the principle using mechanical switches. The animation shows the representations of the three elementary logic functions, with the output represented by a lamp. If the lamp is lit, the output has a value of 1, and if not, then the output has the value 0. We can see that the logical AND is realized by two switches in series. The logical OR is realized by two switches in parallel. Finally, the logical negation is realized by a shorting switch. With the negation, also called an inverter, the open switch causes the lamp to be lit, while the closed switch shorts the current, thus preventing it from flowing through the high resistance lamp. So the lamp is off. Now we will see how one can calculate with these logic functions. A computer uses the binary number system for computing. That means it only knows the two digits 0 and 1. So it is only natural to connect these directly with the truth values true equals 1 and false equals 0. Counting in the binary system works lexicographically with the digits 0 and 1. After the 0 and the 1, there are no further digits, so the first two-digit binary number is 10, which corresponds to 2 in the decimal system. As there are only 2 digits available per place, binary numbers grow much more quickly in length than decimal numbers. Binary numbers were first used by Gottfried Wilhelm Leibniz in the Western Hemisphere. But they were known much earlier in China, as is evidenced by a letter from the year 1703 from the Jesuit Joachim Bouvet to Leibniz. The central square lists the numbers from 0 to 63 in binary notation. A single long horizontal line denotes a 1, and two short horizontal lines denote a 0. Let us now look at the binary multiplication of two binary digits, that is, A times B equals C for binary digits. The basic decimal multiplication table has 9 times 9 equals 81 non-trivial product rules. The corresponding binary table has just one single non-trivial product rule, namely 1 times 1 equals 1. That is a major advantage of the binary system, because only one product rule needs to be stored in the computer. Comparing the binary multiplication table with the truth table for the logical AND reveals that they are identical. Thus, single-digit binary multiplication can be realized technically with the logical AND. What about single-digit binary addition? Here, 1 plus 1 in the binary system yields the two-digit binary number 10, which corresponds to 2 in the decimal system. One easily checks that, of course, 1 plus 1 equals 2 in the decimal system as well. As the result of adding two binary 1s is a two-digit binary number, we must split the result into a carry place, C, and a units place, U. The carry place is given by the logical AND. The units place is more complicated. In the first 3 rows, it is given by the logical OR, and in the 4th row, where both summands are equal to 1, the answer is 0, which is not given by the logical OR. The correct logic function required here is obtained by combining the two logic functions AND and the negation. When both inputs are 1, the AND yields 1, and the negation then turns this into a 0. In the units place of the binary addition, 1 plus 1 would then get A or B, and not A and B. In the first 3 rows of the addition table, The first bracket yields the result, while the second bracket always yields 1 on account of the negation. The fourth row differs in that the second bracket always yields 0. Thus, on account of the AND between the two brackets, the end result is 0. So, the answer is correct. The above logic function is known as the exclusive OR. It has the value 1 only if exactly one of the inputs is 1, and not both. Such a circuit, which yields the carry place and the units place of a binary addition of two binary digits, is called a half adder. For binary numbers with several places, where one has to process the carry place digit of the previous addition, the so-called carry old, one needs a circuit which has 3 inputs and 2 outputs. For this, one uses a so-called full adder. One of the inputs is used to take into account the carry of a preceding calculation. Placing multiple full adders in series allows for the addition of binary numbers with more than one digit.